Let's study 10th standard ICSE Physics Chapter 8, Exercise B Numericals, Resistances in series and parallel and their combinations. In this exercise, there are no cancellations. Let's start with the first sum. Mark it as IMP. Here the diagram is given. The EMF is 2 volt. You can think of EMF as the total potential difference, that is the potential difference across the circuit, as well as the voltage drop inside the cell. Whenever there is no current flowing, there is no loss in voltage or there is no voltage drop. So we can say that the potential difference V is equal to epsilon, that is EMF. Whenever they don't mention anything about a voltage drop or an internal resistance, we can simply think of this as the voltage of the circuit. But here internal resistance is given as 1 ohm. There is an external resistance in the circuit, R is equal to 4 ohm. What will be the reading of the ammeter? That is, it measures current. So how much is the current flowing when the key is open? Well, when the key is open, the current is 0. And what will be the measurement by the voltmeter? Voltmeter always measures the potential difference across the 2 points, that is across the entire circuit. But when the key is open, hardly any current is flowing here. So as I said, the potential difference will be equal to the EMF. So the answer is 2 volt. But the moment the key is closed, some current will flow through the circuit. Earlier, the current was flowing only through this circuit, tiny circuit out here. Even if this key is open, this circuit is always complete. That is why voltmeter is connected in parallel. But now that this key is closed, this circuit is complete, current will flow through this. So how much current will it measure? Well, the formula for current is, simply speaking, V upon R. V upon R. That's the Ohm's law. I is equal to V upon R, or R is equal to V upon I, or V is equal to IR. Just remember this basic formula. But here, we will say that the current is equal to the total voltage upon total resistance. What is the total voltage? That is the EMF. And what will be the total resistance? You see that the external resistance and the internal resistance, they are in series. So that we'll have to add them. We could have done that separately first, but I did it in this formula itself. And I got the answer as 0.4 ampere. That's the current. So remember, whenever you have a series combination, first I need the total resistance, only then we can calculate the current flowing through the circuit. And what is the potential difference now? Earlier it was 2 volt, but whenever current flows through a circuit, there is a slight voltage drop. That's because some of the potential difference is being wasted in overcoming this internal resistance inside the cell. So how do we calculate that? Well, what's the formula of V? V is equal to I into R. I we found out, and R will calculate only the external resistance, which is how much? 4 ohm. So that's 0.4 into 4, 1.6 volt. So you can see that the EMF was 2 volt, but now the potential difference across the circuit is only 1.6 volt. So there is a drop of how much voltage? 0.4 volt drop. And why is there a drop in the voltage? Because of this internal resistance. And how much was that? 1 ohm. Next, the third sum. So again, the diagram is given. Here again, EMF is given 1.8 volt. Internal resistance is 2 ohm. Even if diagram is not given, it's always better to draw it. It makes us visualize the sum and makes it very easy to solve. So we have an external resistance of 4.5 ohm as well as an ammeter which itself has a resistance of 0.7 ohm. What would be the reading of the ammeter? That is the current. We have to measure the current. Now current is equal to total voltage upon total resistance. Total voltage is nothing but EMF, which we know, 1.8 volt. But what is the total resistance? You may want to find that first. Total resistance will be 4.5 plus 0.7 plus 2. You see they are all in series. If I were to draw arrows to check the flow of current, you will realize that the same current is flowing through all these resistances. There is no branching. There is no splitting of current. There is only one path. So they are in series. So again, I have not calculated the total resistance separately. I just put it in the same formula. and I got the answer as 0.25 ampere. So remember, in series, the current flowing through each of the resistance is the same. 0.24 ampere through this, same 0.25 ampere through this, and the same 0.25 ampere through the internal resistance as well. Only in parallel connection does the current split. Next, what is the potential difference across the terminals of the cell, or what is the potential difference of the circuit, external circuit? EMF is 1.8, that includes the internal electrolyte also, but we want the potential difference of only the external circuit, which will definitely be less than 1.8 volt because there is some voltage drop since they have mentioned this internal resistance. So what is the formula of voltage? Where it's current into resistance, I into R. I is 0.25 that we calculated. And what is the external resistance, by the way? Well, it's 4.5 plus 0.5, that is 5.2 ohm. So that's how we get the potential difference as 1.3 volt. You can see it is less than 1.8 volt. So there was a drop of 0.5 volt. That's a huge wastage. Next, the fifth sum. Mark this as IMP. A cell of EMF epsilon and internal resistance R. Okay, so two unknown variables. I kind of feel that this will be like a simultaneous equation sum. So current is given when the external resistance is this much, and again current is given when external resistance is this much. Calculate the values of epsilon and R. Okay, so this is the formula. Current is always total voltage upon total resistance. Total voltage is EMF and total resistance, well, they are in series, so just add them. Current is given in first case, and the value of external resistance is given in the first case. So cross multiply, we get this equation number 1 and 2 variables. Similarly, in the second case, again the value of I and capital R is given. Again we cross multiply and we get the second equation. Note that we can solve them simultaneously and get the values of the two variables. What I have done is, I have noticed that the RHS is the same in the two equations, so the LHSs will also be the same. So let me just write here from 1 and 2. It's important to write that. And now the equation has only one unknown variable. This is a normal algebra sum. Get the like terms together, do LCM, subtract, and get R alone, which is 0.1 ohm. Substitute this value in any of the equations and get the value of epsilon as well, and the sum is over. Now the seventh sum. 4 resistors, each of resistance 2 ohms, are connected in parallel. What is the effective resistance? Easy sum. You should draw a diagram, which would be something like this. Just 4 resistors in parallel. Current entering from here, exiting from here, and each of this is of 2 ohms, 2 ohms, 2 ohms, 2 ohms. So how do we calculate the total resistance in parallel? By the way, when in parallel, the total resistance will definitely be very small. It will be less than 2 ohms. In series, the total resistance is always more. In parallel, the total resistance is less than the smallest value out of these. So this is the formula. And in the end, don't forget to reciprocal it. That's a big silly mistake which students do. Reciprocal it to get the value of resistance in parallel, which is 0.5 ohm. Now the ninth sum. Now this time, there are 3 resistors, each of 2 ohms. They're connected together so that the total resistance is 3 ohm. But how are they connected? We have to draw a diagram. So here you have to do a trial and error. You can do it in the rough work or in your mind. 3 2 ohm resistors. What if all of them were in series? 2, 2, 2. Then the total resistance would be 6 ohm. Definitely that's not the case here, because here the total resistance is 3 ohm. What if all of them were parallel to each other? 2, 2 and 2. Well, the truth is that if all of them were parallel, then the total resistance would have been less than 2. But the total resistance is 3, so this is also ruled out. So I guess 2 of them will be parallel and 1 of them will be in series. Let's solve this and get the answer and check if it is totally 3 ohm. So first of all, they are in parallel, so let's calculate their total resistance. 1 upon Rp is half plus half, reciprocal that, we get 1 ohm. So I can substitute this with just a 1 ohm resultant and 2 ohm. So 1 plus 2, now they are in series. This 1 ohm represents this total resistance in parallel. That is the effective resistance here, which is written as Rp out here. Now the Rs, that is the resistance in series, is 1 plus 2, 3 ohms. Perfect, it matches. So the answer is a parallel combination of 2 resistors in series with 1 resistor. Next, 11th sum. A combination consists of 3 resistors in series, and there are 4 such sets. Okay, 4 such sets. 3 resistors and each is of 2 ohms. So imagine the same diagram. First of all, in one set, if I have 3 resistors, each is of 2, 2 and 2, that's 6 ohms. And this way I have such 6 ohm combinations in parallel. So totally there are 3, 6 and 12 resistances, although I have not shown all 12. This 6 represents a combination of 3 resistors. This is also combination of 3, combination of 3, combination of 3. So you can draw such a diagram for your reference. And now in parallel, how do we find the total resistance in parallel? Well, 1 upon Rp is 1 upon 6 plus 1 upon 6 plus 1 upon 6 plus 1 upon 6. Don't forget to reciprocal in the end. And the final answer is just 1.5 ohm because they were in parallel. Next, the 13th sum. Yes, you have to study such complex diagrams as well. It may look complex, but once you train yourself enough, it will be easy. I see totally there are 1, 2, 3, 4, 5, 6, 7, 8, 9 resistances. Let's start from the innermost resistors here. It's just like solving brackets. If I have brackets inside brackets, we start with the innermost brackets in algebra, isn't it? So here, if you notice, the current starts from here. Let's see. Here it splits into 3 parts. 1, 2 and 3. So that's parallel connection. And all of them will meet each other here and then they will continue their journey. So definitely these 3 paths are in parallel to each other. But the current which splits here, okay, it will flow through 1, 1 and 1 and then come here. That means these 3 resistances are in the same path. So they are in series. Similarly, these 3 resistances are in the same path. So these 3 are in series. And the third part of the current will just go straight. So the current has been split into 3 paths. One path, second path and third path. So I could simply draw this as this way and this way. Let this be resistance in series 1, resistance in series 2. Now how much is resistance in series 1? It is 1 plus 1 plus 1, 3 ohm. So that's 3 ohm here. And this resistance in series 2 is how much? It's 2 plus 2 plus 2, 6 ohm. Okay, 6 ohm. And in between I have 2 ohm. So now these 3 are in parallel. So let's calculate the parallel resistance of these 3. So 1 upon Rp is this. Don't forget the reciprocal in the end, which is 1 ohm. So now this diagram becomes something simpler. So this resistance was here, which is 1 ohm. This resistance was here, which is also 1 ohm. And this is the effective resistance of all of this, which was how much? 1 ohm. So let me just put 1 ohm. So see, this sum has now been simplified. Now the total resistance is these 3 in series. That is 1 plus 1 plus 1, 3 ohm. That's the final answer. That's the total resistance of all of this. So first this was in series and this was in series, then that answer and this are in parallel, then that entire answer is in series with this and this. It's like a riddle. So the more you will practice, the clearer you will be able to see such combinations. Now the 14th sum. A uniform wire with a resistance of 27 ohm is divided into 3 equal pieces. Okay, that means each piece is 27 upon 3, 9 ohm. And then they are joined in parallel. Okay, so parallel connection would be 1 upon 9 plus 1 upon 9 plus 1 upon 9. And don't forget the reciprocal in the end. So now the resultant is just 3 ohm. Imagine if they were connected in series, it would be 9 plus 9 plus 9, 27, which is what was given in the question. So remember, the 13th sum was IMP, mark it as IMP. Now the 16th sum. So the current starts from here, it splits into 3 parts and they meet again. So let's first solve this central part. So that's 12, 6 and 4, they are in parallel. So let's solve that first. And we get the parallel resistance as 2 ohm. And now the diagram can be simplified. We've got only 3 resistances now. The central part, I'm just writing 2 ohm, which is the resultant of all 3 parallel resistances. This was 2 and this was 5. So now what is the total? They are in series, so we can just add them and that becomes 9 ohm. Next, the 18th sum. That is IMP. We have to find, first of all, the resistance between points A and B. Points A and B. So One trick is that just extend it with a wire A and B. Let's say current enters through A and exits via B. So what is the path this current will take? One path is it'll just go like this and come out here. Okay, so there's a 2 ohm resistance out here. The other path is it'll go all the way to D, C, and then come here. That's the second path. That means this path and this path, they are in parallel. But in this path, we have 3 resistances. So they would be in series. 2 plus 2 plus 2, 6 ohm, and this is 2 ohm. So now the diagram can be simplified. I can simply say that current enters through A and exits through B, and in its journey there is a 2 ohm resistance here, and in the other journey there is a 6 ohm resistance, which is a combination of the 3 resistance here. And these two are in parallel. So what is the total resistance then? It is 1 upon 6 plus 1 upon 2, do the reciprocal in the end, it's 1.5 ohm between points A and B. But there is a part B in this question. What if they've asked between A and C? Okay, draw the diagram again. Yes, please draw a diagram in each and every sum. You have to. Add wires at point A and C. So current enters from here and exits from here. So how many paths are there for the current? One is ADC, so arrows, that is one path. And ABC, that is the second path. So again, they are in parallel. 2 paths, so they are in parallel. But in this path, I see the total resistance is 2 plus 2, 4. And in this path also 2 plus 2, 4. So let me draw a simpler version of this now. This is A and this is C. There is a 4 ohm resistance here. And there is a 4 ohm resistance here. And both of them are in parallel. Find the resistance in parallel, reciprocal. And now the total resistance between point A and C is 2 ohm. Next, 19th sum. What's the resistance between point P and Q? If they ask between P and Q, that means I can ignore this 3 ohm and this 3 ohm that is outside. So let's just focus between P and Q. I can see that from P, if the current enters and if the current exits from Q, then it has 2 paths to take. One is straight path and one is this one. So they are in parallel. Yeah, I'm not talking about mathematical or geometrical parallel. It's just a term in physics. But in this path, the total resistance is 3 plus 3, 6. So actually, the diagram can be simplified like this. Entry through P, exit through Q. One straight path resistance is 3 ohms and another path resistance is 6 ohms. So they are in parallel to each other. So how do we calculate that? Like this, and reciprocal. So the resistance is 2 ohm. Great. But in part B, they want the resistance between X and Y. So now we'll have to include these 2 resistances as well. By the way, the central portion we have already simplified, and the equivalent resistance or the resultant resistance of all these 3 ohms is, as calculated, 2 ohms. So now I can simplify the diagram for the part B, which you can draw freehand, that's fine. So we had 3 out here and 3 out here, and the resultant in the center, which is 2, they are all in series. So what is the total now? 8 ohm. Next, the 21st sum. A resistor of 6 ohm is connected in series with another resistor of 4 ohm. So the total resistance will be 10 ohm. And there is a potential difference of 20 volt applied across the combination. Okay, they are in series. Calculate the current in the circuit. Okay, figure out a diagram. And what formula will you use? Think about it. Current. Whenever they say current in the circuit, that means you're saying what is the total current flowing. And the total current formula is total voltage upon total resistance. Total voltage is 20 volts here. Here there is no mention of any EMF, so we can just talk about 20 volts. Perhaps the voltage drop is negligible in this sum, so no need to talk about that. There is no internal resistance mentioned either. So the total voltage is 20 volts and upon total resistance. So what's the total resistance in this sum? 10 ohms, yes. So you may wish to first find the total resistance separately and then substitute in the formula to get the current as 2 ampere. 2 ampere is the current. So let me draw the circuit for you. Here we go. We've got 6 ohm here, 4 ohm here, and the total current is 2 ampere. By the way, in series, remember there is no splitting of current. That means this current, same current flows through this resistance as well as through this resistance. And the total voltage has been given as 20 volt. By the way, the potential difference across this resistance will not be 20 volt. Here the voltage is split in series. So perhaps this will be let's say 12 volt and this will be 8 volt. So the total potential difference is 20 volt. The current is same. On the other hand, in parallel connection, the current is split between the resistances, but the voltage is same. So remember this. So part A is done. Now part B, what is the potential difference across the 6 ohm resistor? That means if we were to connect a voltmeter across it like this, parallel to it, to just measure the potential difference between these 2 points, not the total circuit. The total circuit is 20 volts, but between these 2 points, definitely it will be less than 20 volts. So how do we calculate potential difference, by the way? The formula was current into resistance. Note I'm using V1 out here because V is for the total voltage. Assuming this is R1 and this is R2, you can mention that in the diagram. So V1 is equal to current into R1. Remember, if you're finding potential difference for one resistance, then use that resistance in your formula. Current need not be I1 or I2 because current is same. It's in series. So it's 2 into 6, 12 volt, which makes sense. It's less than 20. And now I know that if they would have asked potential difference across it, it would have been 20 minus 12, which is 8 volt. Next, 24th sum. Diagram is given. They've asked, first of all, what is the total resistance of the circuit. I see there are only 2 resistances, 20 and R. R is unknown. They are in parallel. If I knew the value of R, I would have used 1 upon RP formula to get the total resistance. But we don't know R. So some other way to find the total resistance. What's the formula of resistance? V upon I. A total resistance is total voltage upon total current. Total voltage is given 4 volt. Total current is also given 0.4 ampere. By the way, this 0.4 ampere would split into 2 parts. Let's say 0. Something would pass through this resistance and the other one will pass through this one, and they will meet again and complete the journey. But 0.4 is here connected here, so it's for the entire circuit. So I can use this value. So the resistance in parallel is coming out to be 10 ohm. B, find the value of R. Oh, that's great. We can use the formula of 1 upon RP is equal to 1 upon R1 plus 1 upon R2, where R1 they've given us 20 and R2 they've just given the variable R. RP we just found out resistance in parallel, so we can subtract LCM, do the reciprocal, so we find the total resistance to be 20 ohm. Interesting, same as this one. So I think the current will also be equally split now. So what is the current flowing in R? So as I said, I think it will be equally splitting, so it will be 0.2 ampere, 0.2 ampere, but let's do it mathematically. What is the formula of current? Current is equal to voltage upon resistance. Since we are talking about current passing through this resistance, we'll talk about voltage of this resistance, and the resistance R value 20 ohm. What is the voltage for this resistance? Is it 4 volt? But that's the total voltage. That's fine. The 4 volt will be the voltage for this resistance as well as for this because they are connected in parallel. And in parallel, the potential difference is same for each resistance. It is not split. The current is split in parallel. So the current passing through R resistance, I labeled it as IR. You could have put it as I1 also. Just I won't do because I is total current. So you need to differentiate between total current and individual current, or total voltage and individual voltage, total resistance and individual resistances. So RP, RS, how to use these variables is important to know. So the current is potential difference, which is 4, and R value we already found out, which is 0.2 ampere. Imagine, what if I don't ask Roman number 1 and Roman number 2 and directly ask Roman number 3? Still, you would need to solve all of that. So you really need to understand this very deeply, which will take time, and just doing it once won't be enough. You should rewind and revise again and again till you get the hang of this. Next, the 25th sum. A particular resistance wire has a resistance of 3 ohm per meter. So what if it is 1.5 meter? Then what will be its resistance? And what if 3 such resistances are connected in parallel? Okay, so the A part, first of all, for 1 meter is 3 ohm. So for 1.5 meter, it will be 4.5 ohm. And now what if 3 of such resistances of 4.5 each are connected in parallel? What is the total effective resultant resistance? The formula. And don't forget the reciprocal in the end. So the answer is just 1.5 ohm. Now the B part. The potential difference of the battery, which gives a current of 2 ampere in each of the 1.5 meter length resistances. This is interesting because they are saying 2 ampere current flows through each of them. Please understand, in parallel connection, the same current doesn't flow. The current gets split. And interestingly, in this sum, they are equal, which is not necessary in every sum. So can you tell me now, what is the total current flowing through the circuit? It is 2 plus 2 plus 2, 6 ampere. So that's the total current. And the total resistance also we found out as 1.5 ohm. So now we can find the total voltage. Total voltage is total current into total resistance, which is 9 volt. Incidentally, the voltage across any one of these resistances will also be same 9 volt because voltage is not split in parallel. Next, the C part. The resistance of 5 meter length of wire. 5 meter. Okay, for 1 meter it was 3, so for 5 meter it will be 15 ohm. Easy. But they said twice the area of cross section. Now it's not stretched or doubled or anything like that. That means the length is 5 meters, which is taken into account. We got 15 ohm. And we know now that if the area of cross section is doubled, the resistance is halved. There is less traffic jam. So the answer is 7.5 ohm. Next, the 27th sum. A battery of EMF 15 volt, that's the total potential difference, and internal resistance 3 ohm, okay, is connected to two resistors 3 and 6 which are in parallel. Okay, what is the current through the battery? When they say current through the battery, they mean the total current, the current flowing through the circuit. A diagram here would be very useful, so make sure you draw that. There's a battery out here. Actually it's just a cell, but that's fine. One resistance here and another one here. Internal resistance was how much? 3 ohm. That's too much. Then this one is 3 ohm and this one is 6 ohm. So my first question is, to find total current, I need total voltage. Is that given? Yes, it is. 15 volt. Great, 15 volt. And I want total resistance. That we'll have to find out. First, 6 and 3 are in parallel. So find the parallel resistance, which comes out to be 2. Then that is in series with the internal resistance, small r. Yes, small r is always in series with the external resistances. So I got that as 5 ohm. And now the total current in the circuit is the total voltage upon total resistance, which comes out to be 3 ampere. So the current flowing is 3 ampere. But note that the current flowing through 6 ohm or 3 ohm won't be 3 ampere, because when the current is flowing here, it will split into 2 parts. The bigger resistance will get less current and the less resistance will get a larger current. But the addition of I1 and I2 will definitely be 3 ampere. In fact, we'll have to take into account the internal resistance also for the total current of 3 ampere. But what is asked in the question? First, they wanted to know the current through the battery that we found out. It is 3 ampere. It is a total current, taking into consideration the internal resistance also. Now the B part. What is the potential difference between the terminals of the battery? Yes, the EMF is 15 volt. But the potential difference will be a little less than 15 volt because there is a voltage drop because of this internal resistance of 3 ohm. Some wastage is happening in the electrolyte of the cell because of this internal traffic jam. So how do we calculate that? Well, we know the formula is potential difference is always the current into the external resistance. Current is fixed, it's 3 amperes. That doesn't change in series. And the external resistance is nothing but that RP that we had found out, 2 ohms. So substituting that, we get the voltage as 6 volt. That means there was a voltage drop of 9 volt. That's huge wastage. But these are the numbers for this sum. Now in the Charlie part, they've asked what is the current flowing through the 3 ohm resistance, this one. The entire 3 amperes won't flow through this. The 3 amperes current will split. Some part will go through this and some will go through this. So how do we calculate current flowing through this? Well, what is the formula of current again? It's V upon R. So we just found out it's 6 volt. And yeah, V for this as well as this is same. They are in parallel, 6 volt. Consider this as R1 and this is R2. So I would say that I1 is equal to V upon R1. And I2 is the current flowing through 6 ohm. That is R2. So I1 is 2 amperes. Oh great. So 2 amperes is flowing through this. Out of 3 amperes, 2 amperes is going through this. So how much is left to flow through this? 3 minus 2, 1 ampere. That's right. And it makes sense. As I said, more resistance means lesser current comparatively. So I found the D answer also as 1 ampere. Now the 28th sum is IMP. The diagram is given. So we've got 2 ohms and R ohms in parallel, and that is in series with 4 ohm, and there is an internal resistance as well. EMF is given as 2 volt, and there is a current already given 0.25 ampere. So what is the potential difference across the 4 ohm resistor? Now the total potential difference is 2 volt. But individually, this 2 volt will be split into the voltage out here and the voltage out here because they are in series. In series, current remains the same, but the potential difference gets split. So how do we calculate the potential difference across a resistance? Formula is current into resistance. Current is already given. Same current will reach here. So I would say V1 is equal to I into R1. Yes, I'm assuming this to be R1. So that is why you should draw the diagram and label this as R1. Let this be R2, R3. So it becomes easy for you to solve. So I is the same here. So V1 is equal to I into R1. So I get this as 1 volt as the answer. So out of 2 volt, 1 volt is for this. Okay. Next question is, what is the potential difference across the internal resistance? Basically, they're asking for the voltage drop or small v. Formula for that is fixed current into internal resistance. That comes up to be 0.75 volt. Okay, so that means out of 2 volt, 1 volt is gone here. 0.75 volt is dropped here. So how much voltage is left for this part? That's right, 0.25 volt only is left for this part. So that is a Charlie question. What is the potential difference across this parallel connection, which comes out to be 0.25 volt only. And then the final question is, we have to find the value of R, capital R. If only I knew the total resistance, that is Rp out here, then I could have used the formula of 1 upon Rp to find the value of R, but I don't know what is the value of Rp. So let's find that first. What is the total resistance here? Well, resistance is always voltage upon current, So the Rp is a voltage. How much voltage was left for this part? 0.25 volt. Let's call it Vp. Okay. These terms are just to distinguish between them. I'm calling them Vp. What does it mean? It means the voltage across the parallel connection. You could call it V2 or V3, whatever, but I prefer this. It becomes easy for me to remember. This is the voltage across the parallel resistance. So the resistance of the parallel connection is equal to the voltage across the parallel connection upon current. Remember? Since we are talking about total resistance and total voltage here, so we have to involve total current, which is 0.25 ampere here. So it seems that the resistance is 1 ohm. The total resistance out here is 1 ohm. And then we just use the formula 1 upon Rp is equal to 1 upon R plus 1 upon 2. We get the value of R, which is 2 ohms. So that was an IMP sum. Next, 29th sum is also IMP. There are 3 resistors and they are joined to an ammeter A. So diagram is given here, fortunately, so just copy this diagram. What is the total resistance first of all? Let's start with the current. Positive terminal, it flows. Here it splits into 2 parts. One part goes like this and comes back, and the other one takes this route. Now on this route, the total resistance is 4 plus 2, 6. And in this route is also 6. So let me change the diagram now. It seems it's like this. We've got one route with 6 as a resistance and another route with also 6 as a resistance. So they are in parallel to each other. So first of all, the series was 6, which is in parallel with another 6. So that's the total resistance in parallel after reciprocal is 3 ohm. Now second part, the B part, what is the reading of ammeter is what is the total current flowing through it. The total current is always total voltage upon total resistance. Total voltage is given as 6 volt. Total resistance we have found out to be 3 ohm. So the total current is 2 ampere through the circuit. But note that the current flowing through this will be less than 2 ampere because in parallel the current is split. Now the 30th sum, here totally 5 resistances are given, but that's okay. First of all, R1 and R2 are in parallel, so find that separately. Next, R3, R4, R5 are in parallel, so find that separately. And then those 2 answers, if you notice, are in series. So it's like this. The diagram, the circuit becomes like this. This is the battery. Then there is one resultant resistance. Then there is another resultant resistance, and it comes back again here. Here's the ammeter. So let's call this RP1, parallel connection 1. Let's call this RP2, parallel connection 2. And these 2 are in series. So RP1, 10 and 40, calculate it and get the answer 8 ohms. So let me write here 8. Similarly, calculate RP2. We've got 3 values here, 30, 20 and 60. So calculate it. I got 10 ohms. So write here 10. And then they are in series. So total resistance is 18. There is no internal resistance mentioned. Good. And the current is total voltage upon total resistance, which comes up to be 0.1 ampere.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.